thank you for joining me. Here is the first in an installment of several videos for section 6.3 and 6.4 and so forth. We'll begin in 6.3.1. Here we go. We're going to start in section 6.3. We're going to apply Euler's method to first a linear problem. So we're going to focus on this problem right here, our 6.3, just our basic linear ODE, and we're going to apply Euler's method to that. And so if you can see right down here, that is what you would get when you apply Euler's method to that particular equation. That is what we call F here. So here F of t comma u is really lambda u plus g of t. And now, once we've written down Euler's method, let's go ahead and combine some things. So combine our UNs as you see there. And before we go forward, one thing I want to say is we have an expression for UN plus 1. Now let's go return to what we know about local truncation error for Euler's method for this particular problem. The local truncation error for Euler's method applied to this problem looks like what you see right here. And now you do the usual Taylor expansion. So I'm expanding this guy. I'm replacing this whole thing with u prime at Tn. And so that is going to sit right here. And when I Taylor expand and simplify things out, like I said, we've done this before in class, and what you come up with is that at the nth step, the local truncation error is 1/2 k times u double prime at Tn plus order k squared stuff. For now, what we're going to do is not express it in that form. What we're going to look at is, let's rewrite it as k times my local truncation error. And to begin with, let's start by pulling right off of that top piece that you see here. So k times local truncation error. Let's use this for now. We'll come back to this other highlighted version. So that is going to be this thing right here. So now notice if I solve for UTN plus 1, what I'm going to come up with is an expression like this. So now this double star that you see here, this equation, is an expression for u at Tn plus 1. Now, we have essentially both of the terms we need in order to give ourselves an expression for what the error is, the global error is at the n plus first time step. And so let's write that down. And in this first step, I'm just substituting all the stuff. So this piece came from previous page, and this piece came from above. And now let me combine some terms. In particular, I see this 1 plus k lambda that's common to both un and u at Tn. Keep in mind those two things are different. One is an approximation of the other. Let's recognize that this is simply the error at the nth time step. So now I have an expression for global error at the n plus first time step in terms of the global error at the nth time step minus a little bit of change here, which is my local truncation error multiplied by k. The global error at a given step is always expressible as some version of global error at the previous step times a multiplier, and then sometimes we've got some extra hanging around. So keep track of that because that's going to be the thing that we're going to focus on as we move forward. Our global error is going to get written in this form. Let's start with error at the nth time step. Just substitute from above right there. And now I'm going to do this in a recursive manner. So I have the error at the n minus first time step here. Well, if that's the case, I can just go back up here and refer to 6.7, only now I'm replacing my n and my n plus 1 by an n minus 1 and an n. So now I'm going to apply 6.7, and this thing right here is going to get replaced with this whole thing in the brackets. And so that's just another step. And now I'm going to combine some terms, and when I combine those terms, I have a quadratic power times a global error at the n minus second step. And then I have a couple of terms here that are involving local truncation error at the previous two steps. And so before I move on, I'm going to start thinking about rewriting that in a summation form. So as I move from this step down to the next one, I'm going to apply that 6.7 again here. And then I am going to take these things. This guy is going to be subtracted from that guy and that guy. And so I notice the pattern here about this 1 plus k lambda to a power and these local truncation errors at all these different time steps. So this means what I'm going to do is rewrite this in a form where I have them all in a summation, and notice that I'm just going to use this m as my index so that I can see how the power of the 1 plus k lambda is related to the local truncation error at a given step. And as I clean it up, I notice a pattern. And so hopefully you see the pattern here. You notice that each time I'm increasing the number of steps I have here. Well, my global error at a given time step, that time step is decreasing. And at the same time, the power on my 1 plus k lambda is increasing. And so I go through this process n times, and after all those steps, what I come up with is then a 1 plus k lambda to the power of n. I get all the way down to the global error at my original time step, my initial condition, and then I have an index which runs all the way from 1 to n on my summation. The global error at t0 should either be 0 or maybe I'll have some round off error when I'm computing, but it's going to be very small, very negligible. So let's call it 0 for now. And let's focus on the fact that the global error at the nth time step is really going to be a function of this term right here. So that's the thing we want to bound. That's the thing we want to think about. So I added a little step here. This is in between pages in your notes. This is just to make it a little bit easier for the next couple of steps. Remember this from calculus class? Well, we're going to use it here. All right. Also, a couple of times it's been asked in class, make sure for your reference you understand that the convention is that 0 factorial is 1. That makes the summations or the series nice to write. Okay, so I have e to the x, and related to the discussion that we're doing right now, my x is going to turn into something very specific. my x is going to turn into this k lambda, or k absolute value of lambda, or modulus of lambda. And so everywhere up here that you see an x, just replace it with k times absolute value of lambda. It's a little messier, but it is just the exponential that you know from calculus with a particular kind of exponent. Notice, look at these first two terms, right? These are the first two terms in this series. And so what I can say is that the sum of these first two terms is going to be less than or equal to the whole series. And I'm going to use that in this next equation. It's 6.9 in your textbook, and it just comes from looking at the exponential e to the k times absolute value of lambda in this following form that you see right here. And what we'll see on the next slide or the next page is that we're really looking at this 1 plus k lambda. In absolute value, I can apply a triangle inequality, and I see that once I apply that, I can look at that as just a 1 plus k absolute value of lambda, or complex modulus, depending on the case. Well, it turns out that what you see right up here, that's just these two terms right there. So that is always going to be less than or equal to the full series that you have up there. That is equation 6.9 in your textbook. Okay, so how we're going to use it is in that big ugly summation that you saw on the previous page. We're going to have something that looks like this. And when we do that, well, I'm going to recognize that that's that 1 plus k lambda raised to a power. Well, that's less than or equal to e to the k lambda, absolute value of lambda, raised to a power, raised to the same power. And now once I do that, I'm just going to use some exponential rules to say a power to a power means I multiply my exponents. And then I'm going to rearrange things a little bit. Let's distribute everything. And notice that this guy is less than or equal to 1, right? For m is going to be a positive integer, k is going to be a positive time step value, and absolute value of lambda, or modulus, is always going to be a non-negative number. Therefore, that expression is less than or equal to 1. And now I can take what I know there and say that 1 plus k lambda raised to this funny power is less than or equal to e to the n times k times absolute value of lambda. And for us, in the work that we're doing here in this section, that n times that k, well, that's going to be less than or equal to our final time step, capital T. So we're going to be able to simplify, as you see there in equation 6.10. All right, so that's a little calculus review and some inequalities, and it's also in my notes. You can take a look if you like. What I'm going to do is I'm going to return to what we were seeing earlier, which was equation 6.8 that you see right here. All right, let's take that thing and remember that we're saying our global error at T0 is 0, and we're focusing on that. So now let's do what we always do in numerical class. Let's think about taking absolute values. Let's take the absolute value of the global error at the nth time step. That is this thing right here. And now if I pay attention to what you see here, I've just taken the absolute value of the whole thing back in equation 6.8 and used a little triangle inequality to split it up into its two pieces. This summation is the thing that we really want to focus on. That's an absolute value of a sum, a finite sum. I can use triangle inequality over and over so that the absolute value of that sum is less than or equal to the sum of the absolute value of the things inside the sum. And I apply it again in the sense that now I've looked at the absolute value of the product being the product of the absolute values. We have this thing right here, and we're going to replace it with e to the absolute value of lambda times capital T, multiplied by truncation error. So now, what have I done? I have, if you notice, I have an e to the lambda t sitting here, and then I have an e to the lambda t sitting here. I should be saying absolute value of lambda times capital T, but I'm being a little lazy. So now I'm going to factor that thing out, and you see what I've got left over. I have this expression that is in terms of a local truncation error at each time step, and then I'm adding those things together. So now let's really think about what that is. If I were to say, let me take the max of all of those time steps, the local truncation error at those time steps, then that summation is less than or equal to really just n times that maximum. But what I want to do here is I want to replace this with something simple notation wise, and we're going to call it the infinity norm. It's just so that we can make everything look nice mathematically. And actually, I guess I should say it's the max of the absolute value of the local truncation errors at each time step. So that's going to be called my infinity norm of tau. And then we're going to use infinity norm of u double prime. If you've seen this before, well, we're computing over t values between 0 and capital T. So let's just make sure that we bound our second derivative there. So when we use this maximum idea here, we can say that we can bound the u double prime at Tn by this guy. And so this whole thing that we see right here is simply something that we can call big O of k. All right, now that we've got all those definitions, we're ready to clean up what we see up here in terms of our absolute value of the global error at the nth time step. Let's put it together. What you see here, here's our e to the lambda times capital T. And now I'm going to simplify things down to, oops, that infinity norm idea there. And remember when that n times k comes out, this thing, well, that's really that capital T, right? Less than or equal to that capital T. Since n is some integer getting us between 0 and our last time step. Now, what we've seen here is that, like we mentioned before, this thing is probably pretty small, either 0 or goes to 0 as our time step goes to 0. So we focus on that other piece. That other piece has the exponential times the capital T, exponential of absolute value of lambda times capital T times a capital T. And then we have this infinity norm of tau. So what you can see there is that that piece in yellow is a constant. That means that this infinity norm is giving us our O of k. That means that our global error is going to go to 0 as k goes to 0. Our global error for Euler's method is big O of k, or we call it first order accurate. All right, that's a lot of bounding inequalities. Stay tuned for some more in the next video when we're going to look at some nonlinear problems. Thanks for watching.